And looks like it's recording here. So everybody can see this, I hope. Let me go ahead and play it. All right, so today I'm going to talk about trace element analysis, improving accuracy and precision, because as I mentioned before, they are different things. They can be both improved at the same time, actually, but it requires thinking about these things from first principles. So I'm going to talk about this trace elements both from the perspective of point analyses and also from the perspective of maps, as you can see here. So, so this is just kind of a quick summary of what trace element analysis by EPMA involves. And obviously it depends on everything, of course. There are some basic strategies to improve statistics, high beam currents, if your material allows it, longer count times, of course. You quadruple the counts and you get 2 times the sensitivity because it scales as the square root, of course. And you can also optimize over voltage, so larger interaction volumes equals more atoms if you don't need the spatial resolution. And there are, of course, the factors that affect trace element accuracy, which is the background fits is primarily the main problem, but also interferences, spectral interferences, either on your off-peak positions or on your on-peak. These become dominant. And then, of course, secondary fluorescence from boundaries, that is nearby phases. So we're going to talk about all 4 of those things. And I wouldn't have said it, but, you know, I have to say it. So apparently, choice of standards is not quite understood yet for trace element analyses. And I'll give you an example from the literature. And this was published a few years ago. And here they were analyzing for trace nickel, and they used San Carlos olivine as the trace standard for the primary standard for nickel. And I don't understand this. And the main problem is that the nickel concentration in San Carlos olivine is only 0.3%. And that is just crazy. Your variance in your standard is going to be propagated instantly to your unknown, so you're going to get immediately much worse statistics. And I think this is part of this kind of, I don't know, old-fashioned way of thinking that we need to matrix match all of our standards to our unknowns. And that used to be true maybe 40 years ago. It's not true any longer. Our matrix corrections are really good. They're at least 1 or 2% accurate. And so if you are trying to find a trace standard for your trace element analysis, you're just wasting your time. You're going to introduce further uncertainty into your analyses, and there's problems with it, as I will discuss in a moment. Actually, as it turns out, if you look at the sensitivity equations that are available in all the textbooks, and you look at what's in the denominator and what's in the numerator of these equations, you will see that what you really want for the highest precision analysis is you want a standard that has the highest intensity per weight percent. And that's going to be normally the pure oxide or the pure metal. And so that's all I'm going to say here. And there's 2 other problems with that. The variance, as I mentioned before, is propagated from the unknown, from the standard to the unknown. So that's the other problem. And then the known concentration of San Carlos olivine is actually awful. It's actually like greater than a factor of 2 variance. So you're just introducing further accuracy problems now. And so the solution, as I said, is use a pure nickel or nickel oxide primary standard. And because, first of all, we know what the concentration of that is. And I'll show you what the real problems are. Why did NS get this so wrong? Well, okay, let's just quick review for basics. We're going to plot here concentration from 0 to 100 on the x-axis here and arbitrary intensities on the y-axis. And this line here represents the relationship that we would ideally like to have between our concentrations and our intensities. It doesn't go to 0 at a 0 concentration because, of course, of continuum, which is what we see down here, right there. Okay, so here's a typical absorption curve because we get less intensity than we expect for a concentration given absorption. And then here's what we expect from fluorescence, where we get more intensity than we expect for a certain concentration in a particular matrix. And this varies obviously with the matrix. The main problems with major element accuracy, the dominant effects, are what standard we choose, what primary standard we choose. That's very, very important. That's like a 1-to-1 relationship. the matrix correction, that again is like a one-to-one relationship, and of course dead time when we're working at high count rates. It may or may not be a problem depending on the situation. And remember, these primary standard, these matrix corrections, these are all multiplicative effects, and you'll see why that matters in a minute. For trace elements, it's very different. For trace elements, the dominant effects are background correction, spectral interferences, and boundary secondary fluorescence, as I mentioned previously. And these corrections are subtractive. Okay, so in an absolute sense, they stay constant. Now I'll show you what I mean. So here's a major element. The error propagation is multiplicative, so as we go to a lower concentration, the absolute effect of that error decreases. Okay, so a 2% relative accuracy error at 100 weight percent yields a 2 weight percent absolute error at 100%, but at 100 ppm, it's still a 2% relative accuracy error for the matrix effects, or whatever it is, the standard being wrong, and that's only a 2 ppm because it's a multiplicative effect. So it becomes essentially a non-entity at very small concentrations. It's not important for trace elements. But, and of course we can check the major element accuracy using a roughly, at least, matrix match. You don't want to use Si metal for looking at silicates, but you can look at SiO2 looking at silicates, as long as it's a well characterized standard. And ideally, and I hope this is something we can discuss this summer at M&M, a high purity stoichiometric synthetic material or mineral. For trace elements, of course, it's the dominant effects that I said before, are background interferences and boundary fluorescence. And this is a constant in an absolute sense correction because it's a subtractive effect. And so a 100 ppm accuracy error, absolute accuracy error at 100 ppm yields 100% relative error. So if you're off 100 ppm in your background correction, you have 100% error at 100 ppm. But at 100 weight percent, it's essentially nothing. It's way smaller than any of the effects that you else are dealing with. So these background interference boundary fluorescence are generally not important for major elements. There's always exceptions, but in general, this is a good rule of thumb. So, and then you check accuracy using a zero blank, okay? Because the only thing we can be absolutely sure of is two things. One, 100% if it's a 6/9 pure metal, and 0 if it's absolutely pure and 6/9 pure and doesn't contain the element. So these are the two anchors that we should rest our accuracy checks on. Okay, so in summary, I'm just going to say we want to use a synthetic high concentration mineral for trace elements. We want to check it with a zero blank. We don't want to use dope standards. They are heterogeneous. They are uncertain. We don't know really how good they are. So we do know zero. Zero, it's a gift from the science gods that we can measure a zero blank and therefore know our accuracy to our precision. So as good as you can precisely measure zero, you now know that your accuracy is equal to that precision. That's the beauty of a zero blank. So for example, measuring titanium in quartz, we use Ti2 as a primary standard and synthetic SiO2 as a secondary standard to check for accuracy at zero concentration. Okay, and this is published. I'll get a reference here in a second. And then we also check for boundary fluorescence situations. Run CalcSAF standard. It's actually the standard app that comes with CalcSAF. You can model these fluorescence characteristics and know that they are not a problem. I can't tell you how bad I felt when I went to an AGU talk a few years ago, and I saw all these diffusion profiles being displayed at talks, and they were all fluorescence artifacts, every one of them. It was embarrassing, and then we ended up writing a paper with Paul Asamoah and Borisova. Okay, so for trace element accuracy, what matters is background correction, spectral interference, and boundary fluorescence. And this is something that Mike Jasenovic said to me, and it's absolutely true. He said, try measuring zero, because if you can't measure nothing, you can't measure anything. This is the point about trace elements, and Mike is the master at trace element analyses, so I would listen to him. Okay, and again, everything I'm going to show here today applies to both analytical points and pixels in quantitative X-ray maps, because all these corrections that we're making, the matrix corrections, the spectral interference corrections, these are all part of a double iteration loop here, and this is a wonderful figure from our paper that was published in 2019, I believe, with Julian Allah, an American mineralogist. Okay, just quick overview. Obviously, major elements got a big peak, low background. For minor elements, we have a medium-sized peak and a low background. And for trace elements, we have essentially a flat line. if you think of it 0 as the kind of furthest example of a trace element, then it is a flat line or a curved line, depending on the spectrometer characteristics, but it's no bumps in it. So we want to we want to see these trace elements, um, uh, and what we're really trying to do here is essentially measure 0 when we're doing a trace element. And the choice of the background is going to affect that accuracy. Okay, the choice of the background fit. So you need to have lots of choices in this because it varies. So let's talk about background modeling. There's obviously the simple linear background, which is, we usually assume that, and it's usually pretty good, especially for major elements and minor elements. But depending on the specifics of the spectrometer, and the crystal involved and the X-ray position on the spectrometer, we can get very curved backgrounds, especially at low sine theta conditions. And these curves are obviously not going to work well. These curved backgrounds are not going to fit well if we have a linear background. So that's where you need to think about things. And of course, then you have the nightmare situation, which is from a paper by Mike Trusinovic and Juliana Law, Mike Williams. And you can see that sometimes your spectrum becomes very crowded, even in WDS. And these are an example of fitting more than one background point to a background and excluding certain points here, you can see, where we're not at the background level. And you'll notice there is actually a slight curve to this if you look at it carefully. And so this is all important things to consider when you're trying to get highly accurate trace element analyses. Okay, so how do we deal with this? Well, so the red line here is our peak position, and the green lines here are off-peak positions, which were just chosen to start with, to have something, and now we need to go beyond that. So I'm going to now run over to the software here and see if I can demonstrate this for you. Okay, if I'm going too fast, Annette, you should break in and let me know, but I'm going to try to get through this whole talk. Let's see. So this is an old run I did. Oh, and it's Dale Newberry's birthday today. Isn't that nice? Everyone say happy birthday to Dale. Okay, so we're going to go to, what did I say I'm going to do here? Oh, yeah, so let's plot up uranium, which is another example. It's not the example we were just looking at, but I'm going to just plot up uranium on a wave scan of a zircon. And here you see this, and if we zoom in, and so this is that's the thorium M beta line there, and maybe there's some uranium there as well. But if we zoom in here, we can see that there's a shelf here, and that's the argon absorption edge. And I can go over to here and select absorption edges, and we would see it, but just take my word for it, that is the argon absorption edge. And so when we're trying to model this, if we just use the default values of the background positions, you want to be able to select these. And so what we can do here is click on low here and select our background here. And then when we remodel it, then we're going to get a better fit. So sometimes you can do that if you have room on each side of the peak. His question is this really the background position? And in fact, it's not. In that case, what we really want to do is move our background positions over to the one side of the peak and extrapolate across. And that's something that can also be done using this. I call it same side backgrounds, and so you can actually. Don't know if I want to do this. Yeah, let's go this here. Yeah, so you can actually. I don't have enough background here to actually do this, but you can actually choose a background position that's actually out here, if you will. Whoops, I got to close this window first. And then I can try to extrapolate it. And it may or may not work because these are too close together, as you can see. And then you have to pick maybe a better high side position here. And maybe it works a little bit better. So that's something you might have to do. So the point is that in the reprocessing mode, ProFreq gives you all these options. Now let's look at something different, which is what we saw before, was that curved background on the yttrium. So here's a scan with all these, and you can see the background is highly curved. And if I just model this using the kind of normal straight line background, we're not going to do very well. What we can do, however, is we can select, for example, polynomial fit. And then we can just basically take these values here and we can say, let's increase this one here And let's decrease this one here. And maybe we can move this guy here. And then we can kind of adjust it until we get a good fit at the peak position. See what I'm saying? And this can be applied then to your unknowns in this window right here, where you can assign these, whoops, you can assign these fits. Oh, I'm in my software, not PowerPoint, sorry. Yeah, you can assign it to these samples here. Okay, so let's go continue. I'll just close this just to, and go back to the presentation. All right, so now there are alternative methods, as I've already shown you, and there's some other ones that are basically very different. And there's the multi-point background method, which is where we actually measure multiple backgrounds on our off-peak positions. And then the software can either automatically or you can manually override. You can choose which backgrounds to use, but it's actually the automatic algorithm is very good. And this is an example of it where I've collected 4 backgrounds on each side and said fit the best 2 on each side, and it finds the 2 best fits for that background. And this is can be adjusted manually, as I said, but it really does work amazingly well and gives you lots of flexibility for elements that appear that you didn't know were going to be there, which is kind of why Mike Drasinovic and Julian Alon and Mike Williams, developed this method, because sometimes you're measuring stuff that's heterogeneous and a peak might be present when you did your wave scan, but then another peak shows up that you didn't know about. So this handles this kind of situation automatically. And then there's a mean atomic number background. And you might say, well, why are you doing this in a trace element talk? And it's because we originally thought that, mean atomic number backgrounds were going to be really good for major elements. And it is, because you don't measure background, so you don't have the wasted spectrometer motion, you don't have interferences in your off peaks. But how could this possibly be useful for trace elements? And the reason turns out to be a very subtle mathematical statistics thing, which has gone into great detail in our 2016 American Mineralogist paper. But it basically turns out that when you measure your off-peak backgrounds, you actually introduce imprecision into your measurement. Whereas if you only measure at the peak, and you do a background subtraction using this mean atomic number method, the background is determined by the major elements in your compound. And the major element statistics are very good. So you actually get much better statistics when you use the MAN method and you don't measure off-peak backgrounds. And this technique so it turns out to be great for not just major elements, but also even trace elements when you want ultimate sensitivity. And then you deal with any accuracy issues with the blank correction. All right, so let's look at this multi-point background method. Here's an example of a compound where these backgrounds here weren't very usable, but these backgrounds ended up being quite good, and we were able to do it using as you can see, the iteration mode here. And there it is there. And so now let me show you an example of that. So we load up that, which one was that? Okay, that's the 2016. Try to plan ahead. Okay, so if we go into the plot window now and we look at one of our materials, this is actually a standard that we're using now globally, a rubidium titanophosphate, which is synthetic material. It's really excellent. We've analyzed it for trace elements and it's quite good. So we go to cesium, say, which was the example I think that was shown there. And we zoom in, okay, because you really want to look at that background there. And you can see that if we try to do a fit here, we've got some problems here. This is where we're fitting here with the multi-point backgrounds. We have to, these aren't set properly, okay? And then you can choose the multi-point background here, okay? I have 4 different ones that were required. And so I can start, and the one that's highlighted in cyan, that one is the one that can be moved around, okay? And then you'll see we got a problem here. We got this guy here, which is the 4th one. And we can increase that one. Whoops, that's the other side. Sorry. This is on the low side. Oh, I clicked the wrong button. Sorry. Plus. There we go. And so you can kind of bring it right in. And again, you don't have to use all these points. It'd be nice if you could, and if you adjust them carefully, you can get it so you can use them all. But I'll show you what I mean, and you can assign those then to the samples you have offline. But we can also review these things from this window here. And so if I select cesium again, It can see these are all the points that were in that scan that were required for that data point, and each one is, it's slightly different, but they're all consistent. And optionally, you can load a wave scan here, and I'll load it here just so it makes it easy to see what's going on. And then you can say zoom multi-point here, and then you can see that. And now all I need to do is say, well, just use only 1 point, or here I'll say 2 points for the low side, and then use 3 points for the high side. And it's a much better fit, but I can even say, well, just use the 1 point there because these two are both obviously interfered with. So this is how you can very quickly and flexibly make sure you have the best background fit. Okay. Let's go back to our presentation. And as I mentioned previously, the problem with using off-peak backgrounds is that your variances add in quadrature. When you do the peak to minus correction, peak minus background correction, you actually add your variances in quadrature from the peak and the background. So, and when you're doing trace element analyses, it's important to remember that your backgrounds are essentially of equal statistical importance to your on-peak characteristic emission line intensities. So when you're trying to measure close to zero, you really need to measure your backgrounds actually as long as your peak intensities. So that makes your measurement twice as long. So if only there was a way to measure the continuum background without a direct measurement, and that's now what we're going to talk about is mean atomic number backgrounds. You guessed it. So here's an example of aluminum K alpha, and we're measuring compounds that do not contain aluminum. So MgO, MnO, there actually is a little bit of aluminum in titanium oxide. And we can get a very decent fit. And this background curve is actually very, very reproducible. You can reuse this for many different samples because it's a function of the z bar, the average atomic number. In this case, we're using mass fraction. Nowadays, we would prefer to use the z fraction, which you can read about in one of our recent papers from last year. So because we know the composition of each standard, we know its average atomic number. For the unknowns, we do this calculation for what the average atomic number is during the matrix iteration, because as we get the composition during the matrix iteration of the unknown, we now can calculate the z-bar, resubtract the corrected background to give a more accurate background, and then we keep iterating. And it takes like 2 or 3 iterations, and we've got it. That's that double iteration loop I mentioned, which is also used for the interference corrections. And so because we are not measuring off-peak backgrounds at all, we actually end up having a very accurate analysis, even when there are situations where the off-peak background would fail. And again, I mentioned the double iteration loop here. If we take an example, and there's an important little physics detail here, which is that if we're measuring an element like sodium, we need to apply an absorption correction. And you can see here, this fit is not very good. And it's because we have not applied a continuum correction. This is by default always on in PFE, but you can turn it off just to see the effect. And if I turn it back on, so we get a variance here, a relative deviation of like 11%, and I turn it on, and now we have a much better fit. And you'll notice that it's changed things quite a bit here. And now the fit is much better, as you can see, for the same data plotted with sodium. Okay. So there's another side benefit of mean atomic number backgrounds, which I hadn't appreciated, and Paul Carpenter pointed this out to us some time ago, is that because you're essentially measuring these continuum intensities in your standards, and you don't think that element is present, well, you might get surprised. And one of the surprises you might get is that you might have an interference on the peak position, and that's something that obviously you can't avoid. But you can also just have an undeclared concentration. Here, this is an example of chlorine that was not described in this particular standard, but it actually is present there enough so you can see it fall above the trend here. So you really wouldn't want to include that charisotite in this curve here. But you can see immediately if it falls above the trend, it's either a contamination or an interference. Here's another example. This is looking at a nickel in a bunch of standards. And here, this is an example, again, an undeclared amount of nickel in a natural chromite standard. This is another reason why we don't want to use natural standards because they just contain things we don't know are there, even if we think we know what the compositions are, assuming they're perfectly homogeneous, which they never are, of course. So the point is simply that because we're measuring only at the peak position, when that element is thought not to be present, we can actually get a very good handle on the continuum intensities as a function of average atomic number, which is the x-axis here. Okay, so let me give you a demo of that. And this is just going to be some major elements. I guess we could look at some trace elements as well, I think. Let's see, so that's going to be, this is an old run. And if what was I going to do here? Oh yeah, so first I'll show you the MAN fit window where you saw some screenshots of. So it takes the standards that I'm running and it displays them. And so you can see the fit here, and I can turn off the continuum correction as for sodium, kind of as you saw before. And then I can also select an element like magnesium or iron here. And I wanted to show you an example of an interference. We all know that manganese K beta interferes with iron K alpha. So if I select, but manganese is not selected here. And if I did select it and I update the fit, you'll now see that this 25, which is manganese oxide, is an outlier. And that's because of that spectral interference. So I would unselect that, update the fit, and then we'd be good to go. So that's just an example of that. And then I was going to look at, oh yeah, so we'll look at, so I'll go to the analyze window now. And so our primary standard for calcium, iron, magnesium, and silicon is this 162 NIST mineral glass, which these are excellent standards. It's too bad that they can't be reproduced exactly. But anyway, so this is our primary standard for those elements. If I select 160, which is the other mineral glass, and I click analyze, and this is using mean atomic number backgrounds for all these elements, by the way, except for manganese, because I thought that might be a trace element that I want to focus on carefully. This is a long time ago when I didn't realize that you could use MAN for trace elements, but let's just move on. You'll notice that and one thing that PFE does is kind of nice, it gives you the average analysis of those points there on that standard, but it also tells you what the published values are for those elements in the standard database. And then it will print out the percent variance of those. And you'll notice that, for silicon and magnesium, which is the 162, which is that primary standard, the other primary standard right here, our accuracy is excellent, and 1.7 on the magnesium, 1.1 here. So about 1% accuracy on those major elements. Now, you could say, well, what about trace elements? Well, there's no blank correction applied to this sample because I didn't really think about it. But let's just look at nepheline, which is it's a natural material, but we did analyze it for some minor and trace elements. And if I scroll up because it's displaying the oxide here. So if I look at iron, we measured 170 ppm, but the published value is 1700 ppm, and the published value is 1500 ppm, and the calcium here is 690 ppm, and the published value is 750. And you might say, well, that's 9% off here and minus 8% off here, but let's look at the arithmetic difference here, the algebraic difference here. It's only 150 ppm. Our standard deviation is 160 ppm, so it's essentially within one standard deviation, certainly within 3. And here we're low by 60 ppm. When you have a small number, a large percent variance, relative difference, it looks big, but it's actually smaller than our precision of our measurements here. So this is without a blank correction. You can imagine how good it is with a blank correction. So that's an example I wanted to share with you there. It's kind of amazing how well this works. I still can't believe it myself. Okay. Oh, yeah, that's right. Okay, so let's go on to mapping with MAN. So here's an off-peak map. I acquired these elements here, and hafnium, uranium, thorium, and phosphorus, and measuring on peak, moving off peak, low side, high side, and subtracting them, and then doing the full quantification in CalcImage for quantitative X-ray map. So every pixel calculated quantitatively, corrected for dead time, corrected for background, corrected for matrix, corrected for interferences, corrected for, everything you can think of. So the same analyses that we do for point analyses is applied to every pixel in these maps. And so you can see, though, when we look at something which is essentially probably not much hafnium present, it's essentially a bit of maybe a little bit up here, but it's essentially zero. And we can see that the range of the pixels is going from like minus 0.24 to plus 0.2. And that's because each pixel we're only dwelling, what, 50 or 100 milliseconds? I can't quite remember, but it wasn't that long. So we don't count as long per pixel as we do for a point analysis. So the spread can be quite large just due to the Gaussian statistics. And that's with the off-peak. And now let's take the same exact data, whoops, but now we're going to throw away the off-peak maps that took a lot of time to acquire. And now we're going to just do an MAN background correction. And you can see here now our range has gotten much better. We're only now 0.14 to 0.09. And so, in fact, we're seeing maybe a little bit more detail here in terms of the concentrations here. So we've now improved our precision in half the acquisition time if we hadn't measured off-peak. I did for this because this is just an example of showing how it's done. But you would normally just go right to MAN, acquire one map per element, on-peak element, and then you're ready to go for quantification. And if we have say a blank synthetic zircon, we can apply a blank correction to get even more accuracy. So we get better precision, and using the blank correction, we get more accuracy. And this is just another example of a different zircon. This is these two maps. I ran off peaks, and then that took 20 hours. But then if I hadn't acquired the off peaks, it would only have taken 10 hours. And you can see here, I'm actually getting better statistics on using the MAN. We're actually able to see more detail more clearly. And that was published in 2016. Okay, and now I will show you an example of that. So we're going to look at maps. So we'll pull up our CalcImage software. All right, so let's open a project. And we'll go down to the webinar. Let's see, zircon traces. And I made a copy of each of the maps, and I processed one with off peaks and one with MAN. So I can compare those maps as you just saw in the PowerPoint. But let's just kind of open up these are multiple maps. I'll just choose that one because we saw it already. And when it opens up in CalcImage, you can see these maps here. These are the off-peak maps. Okay, pretty boring. So we can go ahead and just close the off-peak maps, and now we only see the major element maps. These are the trace elements. Okay, we're not measuring zircon or silicon or anything like that. And we're calculating the matrix by difference or specification. So now we have these maps here. And so, for example, if we wanted to see this map better, we could retile it. We can, whatever we want to do. And then, of course, we can also do things to bring out, when you're looking at subtle differences, you can change the color palettes and things like that. And if we go into the specified quantitative parameters, you can see what kind of information we can get. We can get detection limit maps. We can get, of course, atomic percent. We can look at the K ratios. We can even do matrix corrections maps of what matrix correction was applied to every pixel. Of course, we can get a totals map. Now, since this material was not analyzed for the major elements, the totals map isn't very informative, but normally when you're measuring major element quant maps, you definitely want to get a totals map and see how well you did, because we use the totals to get an idea of where we went wrong. Okay, so that's kind of important. And you can also plot up your stoichiometric oxygen, your ferric ferrous oxygen, and element-wide differences. And so this gives you a lot of flexibility here. In this particular case, we have off-peak maps here, but we're not using them because we've already said we're using the MAN correction. So that's pretty flexible. That's pretty nice. And just to kind of show you how this works, I'm going to actually start calculating these quant images here. And it's going to say, you want to start these and make sure everything's done. And you can say yes, and you can open up this little log window here, and you can kind of see what's going on. And here are the, and it's loading the MAN backgrounds, and now you can see, and you can see I'm just doing zirconium silicate by difference there. But these are the pixels here, and you can pause it. And let me pause where there's a, so there's a thorium, hafnium, uranium, and phosphorus, and yttrium. And then the oxygen, zirconium, and silicon is added by specification because you do want to have that matrix correction, even if it's a trace element, just because, it's better than not having it. And we can continue that. You can see the speed of this. This is actually going to take 13 minutes because we got the log window up here. If I close the log window, you'll notice that it speeds up dramatically in terms of the calculating each pixel. And when it gets to the end of the line, it'll make a new estimate. And you can see it already went down to 8 minutes here, and it will keep improving as it goes. So I'm not going to let that finish just because we're going to save time. But if we want to then see our results, which have already been calculated, I can export these to a project, and I can say, all right, let's output the quant maps. And it made a script, okay, automatically. And I can say, do you want to run that script? And this is why we supply the Surfer and Grapher software with Pro for EPMA, because you have so much flexibility here. It's really nice to have this capability, as you'll see here. So all this report generation is really trivial with this scripting method that's in CalcImage. And of course, you can see your backscatter and your CL if you did that. And I should point out that you can go to this map now and you can reopen it. And now you can customize it as much as you want. You can say, well, actually, I don't like that color palette. I'm going to use, they have something really weird here. Green, purple. Okay. So you can mess around with it. You can also say, okay, I don't really want a y-axis on this one because it makes it look too busy. So I can say, go ahead and turn off the left axis here. And so now I don't have that. And you can do that for each one of these. And so it makes it a little less busy. Oops, sorry, left axis here. And so it gives you a lot of flexibility in terms of generating reports. And of course, you can then make PDFs of this, JPEGs, PNG files, whatever you want. All right. Okay, let's get back to our presentation. All right. Did I do everything I wanted to do? Yeah. Okay. So interference corrections. This is something we started back in the 90s. People weren't doing this right, so we said, let's deal with it. And basically, it turns out this can be fully quantitative. The interference correction, it should not be using the old-fashioned ratio method of the intensities. You want to base it on the concentrations, because what matters is the number of atoms present, not the apparent intensity of that interfering line. So here, this little bump right here, this is our interfered element. This is the one we care about, so that's element A. And then we have the interfering element, which is element B. And then this is a secondary emission line of that B peak there. This happens to be overlapping on our A line. And this is basically, so this, if you'll notice, if you ignore this right here, you'll see that this is just the normal, fully quantitative expression that we use to calculate concentration of our standard, the ZAF correction or FibroZ. This ZAF is just a placeholder for whatever matrix correction you're using. The unknown correction on for the unknown, the intensity on the standard. And then this term here is applied during the iteration. So we first calculate a composition, and then based on the compositions, we calculate the interference quantitatively, because we actually need to know the concentration of the interfering element. So that's why you have to analyze both the interfered element and the interfering element. When you have both of those quantified, now it's very simple to calculate the interference correction. All right, and that's that term right here. And the S bar is the interference standard, matrix correction interference standard. The beauty of this is that, so by definition, the standard you use for the interference correction has to be different than your unknown. Okay, it has to contain a known concentration of the interfering element, but none of the interfered element. So it's going to be different than your unknown by definition. And then and then once you have that, it doesn't matter how different the matrix is, because we do a full matrix correction from the uh, interference standard to the unknown, and then, of course, to the standard itself. So all this is done completely quantitatively. And this allows us to do something, because it's iterative, we can actually do these weird situations where you have a cascade interference. For instance, people who are analyzing titanium, aluminum, vanadium alloys, where titanium interferes with vanadium, and vanadium interferes with aluminum. What is it now? I can't remember now. Yeah, titanium interferes with uh, uh, vanadium, and then vanadium interferes with chromium. And so it's a three-level interference. And so normally in other software packages, you have to actually analyze them in that order. You have to know what the interference is to begin with. But in an iterated model like you have here, the order of the elements doesn't matter. It figures it out. And that is also true when you have a pathological situation where A and B both interfere with each other. For instance, like barium and titanium, or lead and sulfur, or molybdenum. They handles those situations automatically, as you'll see. So yeah, so let's kind of do an example using point analyses. All right, let's see what I got here. Let's do this one. And so this is, I'm going to take an example here of pyrite, and we analyze here for, as you can see, we're analyzing for iron, sulfur, copper, molybdenum, zinc, whatever, silver and calcium. But the important point here is that this is a pyrite, okay? And it happens to be a standard that I developed at Berkeley. It's the cleanest, purest pyrite I could find in their entire collection. I analyzed like 10 different pyrites, and this was the cleanest one. And it's very clean, and there is no molybdenum in it. I think it was done by AA and XRF, and I can't, this is not, I mean, then we did further analyses on it, but there's no molybdenum. But we're getting 1.8% of molybdenum here. Well, that's not very helpful. I mean, if molybdenum is an important trace element, I mean, it's an economically valuable element. And so if you think there's 1.8% in your pyrite, you're barking up the wrong tree. So what we want to do then is we want to go into our standard assignments. And you'll notice here we've already got molybdenum interfering with sulfur, and we've got sulfur interfering with molybdenum, as you can see. So we're already dealing with this very nicely. And so we click on, say, that molybdenum being interfered by sulfur. So here's molybdenum, that's our analyzed element. Here is sulfur, and this is our interfering element. If we wanted to confirm that that was indeed the case, we can run a quick model, and we can see that the on-peak position for molybdenum is very close to the sulfur K alpha 1, 2. So it's a very large interference here, which is why we're getting 1.8% there. So when we assign this, if I click OK here, it'll automatically assign that interference correction. But I'll show you how to do it manually, because every correction the software makes is automatically accessible here at a global basis. So you can make all your assignments, and then you can turn it off and on to see whether it works. And we saw that we had a 1.8 weight% of molybdenum here, and now I'll just turn on the interference correction, okay? And now reanalyze it, and now you're going to see, basically, you see 0 with some variance there, and it's 100% correction. Of course, this is our standard for the interference correction, but for other materials that contain sulfur, we'd see a similar thing. So that's good. So let's go ahead and close that. Go back to our, okay. And the same thing for maps. So these are some maps where, unfortunately, I didn't map copper for a reason I can't remember. I think I was already using all my LIF crystals. So this is without the interference correction in a quantitative map. And you can see from the sulfur that this is the pyrite phase right here. And this is the chalcopyrite phase. And if you look at molybdenum, we're getting a lot of molybdenum in both these phases here. So let's go ahead and apply the interference correction. As you can see here, now these two phases are statistically similar. And in fact, the interesting thing is that, whoops, sorry about that. And this is all matrix corrected, of course. And the interesting thing is that this phase here is now popping up. So let's look at that in more detail. So here's our, without an interference correction, is our pyrite, our chalcopyrite. we're getting about 1.8, 1.9, here about 1.2 in the chalcopyrite because it's got a little less sulfur. And then we look at our corrected for interferences. And now what you can see is that we've got this new phase here, which is about 0.2 weight percent molybdenum. This is actually the phase that we were interested in if you're looking for molybdenum. And that was published quite a long time ago, but it works. Okay, and now we can look at maps. And I think I'll just do this. Okay, we'll close this project. And we'll open a new project. And here's the map here. Yeah. And then I did it, made it. That's a really good trick, is to make a copy of your database and you can reprocess it different ways and compare them easily. Let's see what I've got here. Yeah, so same standardization. Go ahead.
Just keep in mind the time. But
okay.
You're still good.
Well. Yeah, and anyone who needs to leave, feel free to leave. We're going to record this. Hopefully we're recording this. And then hopefully we will put it up on the forum pretty soon. So you can watch it at your leisure. Okay, so I will just say here that we got, so we can close the off-peak maps because we're not using them, because we're going to use the MAN method again. And we can go into and it's the same standard assignments that we had before. Okay, so same standard assignments we had before. It's the same dialogue. It brings them over from Pro for EPMA, so that's all done. And I already did the export to Surfer, so I'll skip that. And so, yeah, so I'll just skip that, save time. All right. Hope everyone's enjoying it. Okay, here's a small problem, and I wasn't going to bring this up, but somebody pointed out to me, and I can't say who, but and this is something I've talked about myself, and I wasn't going to mention it, but some softwares want to zero out negative intensities from your analyses. When you do the net intensity calculation, if you get a negative number, you shouldn't do that. Don't do that. Because if you try to take the average of a truncated distribution, you're going to get an offset. And so these red intensities here are the normal. If you're trying to measure zero, for example, this is a simulation, but if you're trying to measure zero, you want to see that distribution around zero. So that means that some of your intensities are going to be negative and some of your intensities are going to be positive. That's the red ones here. If you force all these guys to be zero, as in the blue here, then your average is going to be somewhere around here. You're going to think you have a concentration when you don't. So don't do that. It means you have a different problem. So let's just look at this really quickly. So this is all the intensities here. This is all the intensities here. And you can see that these guys are all negative. Every one of them. No positive intensities at all. And in fact, if I force those negative intensities to zero, I've got a zero here. They're all zero. And that's an artifact of forcing that to zero. What you want to do instead is figure out what the problem is. Why are these guys all negative? That's a problem. I mean, it's not a big negative, but it is consistently negative. Maybe it's a problem with your off-peak interferences. Maybe you got a line showing up where you're trying to measure the background, as we looked at before with the modeling of the backgrounds. Or maybe it's something else, okay? Maybe it's something else. What could it be? Well, this is where the blank prediction can help you. So again, as Mike Trasinovic said, try measuring zero, because if you can't measure nothing, you can't measure anything. So here's an example of a titanium and quartz, and there is a hole in the background here, not the bottom of the sea, but the background. And this has been noted by people for many years, but now we can finally do something about it. This occurs in several element situations, measuring gold in the presence of iron. In this case, this hole is from secondary Bragg diffraction of your PET crystal. In the case of the iron gold thing, it's actually a sample absorption edge that causes a hole in the continuum. So whatever it is, the background blank can handle it. By the way, if it's a problem with the spectrometer, you don't even need a matrix matched blank. You can use any blank. If it's a problem with the sample that's causing the continuum artifact, then of course you want to have at least a roughly matrix matched blank. So, pure quartz for quartz or pure zircon for zircon or whatever. Okay, so this requires a blank. So what we're going to do here, I'm going to blast through these because we don't want to take too much time. But you can see here that we're getting excellent precision. We're getting like this is a 10 ppm here, 5 ppm here, 7. These are really good sensitivities. But oh my God, what's going on here? These guys are very statistically different. This is 28 ppm negative. That was the one we saw before. So there's something going on here. Okay, which spectrometer is correct? Okay, we got to figure that out. And the way you figure it out is using the blank correction. And the blank correction, the level can be non-zero. I highly recommend that you get a 0 blank. The example you're going to see here is my quartz blank here. Synthetic quartz has got 1.4 ppm from ICP-MS. So it's not exactly 0, but it's very close to 0. But it is applied iteratively. And so here's the example here. Now this is the blank correction. I'm using this other sample, other quartz synthetic, as a test, and you can see that I've declared 1.4 ppm for all the blank levels, and the blank values, this is the amount of the correction that it's performing. You can see it's essentially all of that. And now you can see we've got now a beautiful variance here. It's very close to 0, but the variance is larger than our difference from 0. So now we have agreement between all 5 of our spectrometers. We're measuring titanium on all 5 spectrometers, and we've got very reproducible results, good agreement. And I just will mention that, there's some confusion about standard deviation and standard error. I'm not going to go into it, we don't have time, but the standard deviation is what you really should quote for the average, for a single point in a sample. The standard error is what you really want to quote for your average. So if you're comparing single points, use standard deviation. If you're comparing averages of samples, use the standard error. And this becomes really obvious when you're looking at X-ray maps and you're averaging lots of pixels. It turns out if you have consistent statistics, no matter how many points you average, you're going to be seeing the same standard deviations, but you will get an improvement if you use standard error because we want to see what the improvement is by averaging more pixels or points. Okay, and now you can see our detection limits are the same. Okay, they haven't changed. We haven't changed anything about the statistics. We've just improved the accuracy of our trace element analysis. Okay, so could we do even better? Well, yeah, we can. We can use the aggregate method. And so this is a little schematic that Annette put together for me. And this is you could measure calcium if it was a trace element 60 seconds here on one spectrometer. But if you measure it on 20 seconds on multiple spectrometers, you can combine those as though they're one giant spectrometer and get the similar statistics, okay, in much less total time of your analysis. So here's an example where we've now taken those 4 other spectrometers and combined their intensities into this one spectrometer here, one giant spectrometer. And it doesn't matter if you're using PET crystals and LIF crystals, photons is photons. So as long as it's the same photon at the same KeV, the same emission line at the same KeV, you can combine them together. The physics is all the same. Physics doesn't know anything about what crystal you're using. And now you can see we're getting a 99% confidence of 3.1 parts per million. And I got here 2.4 ppm plus or minus 1.4 ppm. I really want to show this. I'm going to beg for your indulgence and show you really quickly something kind of cool. So if I plot up my SiO2 standard, my titanium standard, and I'm going to look at my large PET crystal because that's the one with the artifact. If I plot those up, green is the titanium, that's the primary standard, and the blank standard is the SiO2, and I zoom in here, right? Okay, that looks pretty, there's just nothing there, nothing there, nothing there. Let's zoom in a little bit more. Oh, wait a minute. What's these little bumps here? That's weird. Let's zoom in a little bit more. Oh my God. And that's when you see them. So you can't see these unless you really are looking for them. But the blank will tell you instantly that you've got that problem. Okay, so keep that in mind. And then if I go to the analyze window here, I can analyze this guy here. Is this the one I want to do? Whoops, that's not the one I want to do. Sorry. Let's skip here. Okay, so here's I did an analysis at 960 seconds on peak and 960 seconds off peak. These are all using off-peak backgrounds. I now know I would do this using the MAN background method, but let's just go with it. So there's my 2.4 ppm plus or minus 1.4 ppm, and I've combined all these guys together, and I wasn't going to show this, but if I went and did another analysis using 1920 seconds on peak and then 1920 seconds off peak, if I analyze that, then lo and behold, I get 1.4 ppm and plus or minus 0.6 ppm. So that's what we call spurious accuracy. It's too good to be true. So I wasn't gonna show you that, but I couldn't help it. Sorry about that. Anyway, it's just amazing what you can do if you really apply the tools that we have available. Okay, let's go here. And so we can do the same thing on maps. We can combine spectrometers on maps. And this is an example that Aoife McFadden did at the University of Adelaide. She did looking at sulfur and other trace elements in these otoliths. And so here's just a raw data. Okay, this is the raw data. But then she combined the data from multiple spectrometers and quantified it. And now we get a much better map here. And again, didn't take any longer. She just had to measure that element on multiple spectrometers. Okay, so this is the part of the talk which, we could stop here, but I'm going to keep going because all you people are really hanging in there, I'm sure. So the problem is that secondary fluorescence from boundaries. And I mentioned that I went to the AGU talk and saw these so-called diffusion profiles, and people were calculating thermodynamics of melts with them, and every one of them was a fluorescence artifact. Every one of them. They were all just calculating garbage. So what can we do about that? Well, first of all, we need to understand the problem. And the problem is very simple, is that the electrons travel a limited distance in our sample. And that is called our interaction volume. However, X-rays generated by the elements in that volume travel much further, okay? Many times further. I'll show you an example. It will blow your socks off in a minute. And these X-rays, they can be characteristic X-rays. They could even just be continuum X-rays. They travel in all directions. A little bit anisotropy for the continuum, but it still travels mostly in all directions. And so if we're measuring a trace element in phase A, and there's a major amount of the element that we're trying to measure in element B, as we get closer to this boundary here, well, we're going to start picking up emissions from this phase here. And our Bragg spectrometers, certainly our EDS spectrometers, cannot resolve that spatially. So we're going to see those X-rays. You've heard of system peaks. Well, this is kind of related to that, except it's even worse because you got to model it to find out what's going to go on. This was published a few years ago, and I highly recommend reading this. We've got some great examples in here. And there's also the paper by Borisova et al. So how bad exactly could this be? Well, here's an example that Wark and Watson did. And they basically, this is the red line is the calculated fluorescence effect from PNETMA. Okay. And the circles here are the ones that were measured in their lab. And you'll notice it starts to fall off this curve here as we get further away from the boundary. The boundary's over here. And that's because of Bragg defocusing. And I'll explain that in a minute. But basically, if your boundary is at right angles to your Bragg crystal, as you move away from the boundary, you will get Bragg defocusing. If your boundary is like this, though, you will get no Bragg defocusing because the beam moves in this direction and the crystal doesn't see Bragg defocus in that dimension. So that's something that you can do. You can correct for that yourself, and I'm trying to add it to the software right now. Okay, so yeah, so this is down at the 10 ppm level, and of course we know that we can get down to this kind of level from the silica, titanium, and quartz paper. And then for major elements, I mean, for trace elements in other situations, like where you have actual characteristic fluorescence, as you do here, where you're measuring iron, you're measuring nickel in pure iron. No, where you're measuring iron in pure nickel, sorry. Then you will get the nickel emissions will actually stimulate the iron K line very very intensely, and that's why you can get up to like 5 weight percent here. So that's huge. That's a huge effect, right? 5 weight percent, and it's a complete artifact. Now that's at 1 micron from the boundary, but even at 10 microns, we're looking at like, around 0.3 weight percent, something like that. So these are big effects. And even when you have a situation where there's no characteristic emission that's causing a fluorescence, in the case of measuring nickel K alpha and pure iron, just from continual fluorescence, I'm sorry, let me rephrase that. So at 10 microns, we're getting 1 weight percent of apparent iron in pure nickel next to iron. Here we're getting about 10 microns, we're getting about 0.3 weight percent just from the continual fluorescence. So these are big effects, can be big effects. Not always though. Okay, so what about trace elements? Okay, so here in geological materials. So here's an example of calcium K alpha measured in an olivine, a Smithsonian olivine, adjacent to diopside. So we've got some major calcium in diopside. And as we approach that boundary, you can see we're getting weight percent wise around 0.1 weight percent, so 1,000 ppm. The K ratio is much higher, of course, but that's because we're using a standard for calcium, which is a lower concentration. But here the actual weight percents are around, and there is some calcium in the olivine, so that's why it doesn't go to 0 here. But the contribution just from the boundary is in the blue triangles here, and you can see it's still around 1,000 ppm. Here's an example of chromium K alpha measured next to a chromite synthetic, which could be a chromite, and we're getting around 9,000 ppm. So these are not insignificant, and as you can see, even at 50 microns, we have not gone to 0. So we have tools for this. We can actually model this, as you just saw. We can put in our beam incident material, we can put in our boundary material, we can put in a standard for the element, plot the element up, and here we can see exactly what's going on. We can make a prediction about what kind of problem we're going to have. And maybe it turns out we don't have a problem, but at least we will know now if we have a problem. We had such a problem with secondary fluorescence from rutile grains in our quartz experiments that we ended up using FIB to remove the experiments and then analyze them in the probe, placing them on a TEM grid and then analyzing them in the probe, just so we didn't have that secondary fluorescence. But we can now correct for that, actually. And then here you can see, we can even have a weird thing. It's a negative artifact. So if you're analyzing a sample, a material that has a lot of internal self-fluorescence, and you're sort of approaching a material that doesn't have that self-fluorescence, well, now you can actually lose intensity, apparent intensity, as you approach that, as you approach that boundary. So that's another unexpected artifact that you might see in highly fluorescing, self-fluorescing materials. Okay, so let me just run this really quick. So this standard software, by the way, is free. This comes, you can download it from CalcSAF right now, and it's available online at a number of different locations. Let me know if you can't find it. So I'm going to do something that a national lab approached me about a few years ago, that they had a problem. And I apologize for being so far over. Okay, and then I'm going to put in a zinc standard, and I'm going to analyze for zinc. And I'm going to calculate it. So it runs the model, and this is for creating new materials, because it takes 10 hours to run each material. But once you have it calculated, you can calculate it for any takeoff angle, any kilovolts for any X-ray. And so you can see we're getting up to 1.4 weight percent of apparent zinc in aluminum as we approach zinc. Okay, and as we move away, here we are 50 microns away, and say, well, okay, how far do we have to go to hit 0 there? So let's put 500 microns in and do 500 data points. So we recalculate it. Again, the Panetma calculation, the Monte Carlo calculation has already been done, so this takes just seconds. And there we go. And so we say, oh, okay, finally we reached 0. Or did we? Let's do a log scale. And even at 300 microns, you can see here, we're getting 100 ppm, which is easily detectable in a microprobe, 300 microns away. So just beware. All right, let me just finish up. We've only got a couple more slides. Okay, so we can actually correct for this. I'm going to skip the correction. It's in PFE. It's very simple. You basically draw the boundary. You draw the boundary right here, and you define, because you don't have to, you could draw the boundary, or you can even just specify a position for the boundary. Okay, it's very simple. And then you can even see your data points there, and you can actually now quantify it. And you import a calculation like we just did. You import that calculation into the ProPrePMA file, and it saves it for you automatically. Okay, so this is a new feature that we put in last year, and it works. In this particular case, I couldn't get an exact, this is supposed to be pure iron and pure nickel, and I couldn't get them to quite meet together. So there's a slight overcorrection in the data, which we still have 17 people hanging in there. All right, I'm going to do it. Barely hanging in there. Well, that's the nice thing about being talking to my wife here. It's a nice thing about being the last speaker, right?
Yeah, but
So,
still leave some time for questions.
oh,
And I
I'll stay
think,
here. I'll stay here as
yeah,
long as people want. Okay, so if
people
I'm
might
going to,
get to their saturation, but anyone who dialed in knows that we are not on time.
right, right. So if I turn off the boundary correction here, I'm getting about 0.4 weight%. You can see right here at the boundary. And if I turn on the boundary fluorescence correction, that, by the way, is right here. I'll just turn it on in the analytical window here. Use secondary boundary fluorescence correction, and I run it again. And I'm slightly overcorrecting because, again, there's an air gap, vacuum gap between the two phases, but it's much better than it was. And I consider it a victory whenever I do something improved. All right, almost there. And as Annette Vonderhant is documenting in a paper in preparation, there is these TDI effects can also be a problem for trace elements. And so we need to think about how our trace elements may be beam sensitive. And so this is something that can be done. We can do this. And then even trace carbon, we can do trace carbon by using TDI curves. Here's the data quantified for carbon, but without the TDI correction. We do the TDI calibration, and this is kind of amazing to me. This is about 8 hours of maps. So here's a map, there's a map, there's a map, there's a map. These are all scanned maps, okay? And this is the starting at the nth pixel and following through and extrapolating back to 0 time. When we do this, we get a very much nicer carbon map. So we can do trace carbon now quantitatively without any crazy calibration curves, although calibration curves can work too. And then I think I'll end on this pretty picture, just to mention for trace elements, sometimes the truth is buried. And so this is an example of some quartz where we analyze these different elements for John Mavrogenes at ANU. And you can't see much going on. So we have an option in the mapping software where you can say, turn on log weight percents. And now all this incredible detail pops into view. So I'll leave it there, and because it's a pretty picture, and I will take any questions, or we can open up for general questions if people like. Thank you,
Thanks,
everyone.
John. Yeah, amazingly, most people hung in there. So thank you very much for everyone who's been staying with us. And of course, now I have a truck coming in the back. And so we have a couple of questions, and I will read them out specifically also if it's up on YouTube so that people hear the question. So there's one, when does the accuracy gets worse than the precision for trace element measurements using man without blank correction?
Oh,
When
yeah,
measuring less than 100, 250?
yeah. So it entirely depends on the average Z of the material. And what I can tell you from many years of experience that for typical silicates between average Z of 10 to 20, which is basically from magnesium oxide to your, transition metal oxides, you are going to start to see that the accuracy is limited around, it depends how careful you are. I know that people who do it very carefully and do better than this. I'm thinking of people like Andrew Locock who are very, very meticulous in their MAN curves, but you can get around I typically get around 200 to 300 ppm accuracy without even trying. So perfectly good for major elements and even minor elements. But to get below 200, 100 ppm with MAN, you definitely want to use a blank correction. And as I mentioned before, that blank doesn't have to be perfectly matrix matched unless the artifact in the continuum is specific to a specimen that you're using, like the iron and gold gold and iron situation. But yeah, 100, 200 ppm. And then I know that on the forum, I believe on the user forum, I think Carson Goman posted a number of examples where he was looking at like uraninites and other rare earth compounds, and he had really interesting results looking at these high Z materials and how accurate the mean atomic number background was uh, compared to off-peak backgrounds. And he basically found that he had fewer problems with the mean atomic number background because there were so many off-peak interferences he was running into that actually the MAN method turned out to be better, gave him better sensitivity, and saved him time. So what's not to like about that? But you can always run the comparison yourself. I'm open to people doing that.
Another question. There are a couple of just people being amazed by what they seen using this, and Steve is a huge fan of MAN too. I'm not sure if it's a question by Steve, but he's asking multi-threaded CalcImage. To my knowledge, CalcImage is multi-threaded. You can
Well, it's
open
not.
or not, but you can
CalcImage is
open
not.
multiple instances.
Yes, yes. CalcImage is not multi-threaded itself, but you can have multiple instances of CalcImage running on the same computer. So you can, and in fact, and I should point this out. Let me just share my screen really quick here again. When you run a CalcImage, when you create a CalcImage project, there is a is it? It might not be. No. So let me go to another folder. When you run a CalcImage project, it creates a batch file that contains it. And every time you open a CalcImage project and output a new project, it creates an additional a batch, adds a new line to the batch file. And then you can just run that batch file, and it will run all the do all the calculations overnight or whatever you want to take. Depending on how many pixels you have, I mean, it only really takes maybe, depending on the number of elements and depending on the, let's see if I can find that batch file here. Maybe if I sort by type here, it will say batch file somewhere. Anyway, you can definitely run it as a batch file. And
The last
then,
one.
yeah, the last one. I don't think that's it, though.
No? Okay.
I don't think so. Uh,
Well, I mean, maybe we can have a webinar at one point about all the batch versions. Like,
Yeah, I mean, it's documented on the forum. I know that, but it creates a batch file. I'm not finding it here, but I think it's because I only ran one. So when you open up your first project, it creates a new file, and then only when you do second and third and fourth projects does it add lines to that. But yeah, that's a feature. But you can also just run them in parallel. It doesn't hurt. Yeah. Okay.
okay. But yeah, they would like to see multi-threaded. I don't know how difficult that is, but
It would be impossible
okay.
because I'm using an old compiler. It doesn't support multi-threading.
Ah. Okay, then yep, Steve makes some good comments about never forcing negative to zero. There was also the question like what will be on the forum. We get a copy of the Q&A questions and comments and as a text and we will post these also to the forum as so that people can also read what was not answered in videos but just put in there. And I think then what else do we have? One anonymous attendee was saying, totally hanging in here. I would like to see the boundary correction in action.
Well, I did run through
The
it very.
masses are asking for more and longer video content.
Well, so I did run through it very quickly. Okay, do you want me to do it now?
Or we could also just say let's make a dedicated. I think it's an important enough subject to actually have like a dedicated 20-minute
Well,
tutorial and all
yeah,
that, rather than
yeah, yeah,
tacking it on here.
yeah.
If
I think yeah, a secondary boundary fluorescence uh, webinar or tutorial would be a great idea because it is a complex topic. The first step, I just can't emphasize this enough. The first step is just download CalcSAF, run the standard application, go into the and there's a nice little tutorial on the forum that explains how to do this. You can just do it mouse click by mouse click, but go to the analytical menu. Open up your standard database so that when you download Profi or CalcSAF, as a default installation, on any computer, you get my database, but you can use your own standard database. It doesn't you can use any database. In fact, when you go to open the database, you can actually open up. You don't have to open the standard database. You can open up the American Mineralogist Crystal Structure Database, DHZ, DANA's, or minerals, NIST. So you can do all that kind of stuff, but you can just open the default one. And then you just go to this analytical menu right here. This is the full PNETMA GUI, by the way. If you want to do full calculations, including secondary fluorescence from like grains, inclusions in phases, and weird geometries, and I mean, for the ultimate, calculations, if you don't want to write your own Fortran and scripts, this GUI is really nice. It's very easy to do it. And then you get a nice full spectrum. You can open up, a previous project. There's all kinds of, yeah. Anyway,
good, okay, then
yeah.
I think in terms of like actual questions to it, that would be it. And I think we still have a few people in here, but I'm sure that everyone learned a lot and is filled to the brim with information. We will post the PowerPoints to the forum. The video will be there and on the YouTube channel. I will add the Q&A as well. So if you want to revisit anything or watch it at a slower speed or watch it at a faster speed so that it makes it look like as if we were on time, then you will have the chance to do that. And yeah, thank you for joining in. There will be other topics. We're also open to suggestions of topics that people would like to see covered. And
And
yeah,
I should mention, Annette, that we're doing two formats right now. We're doing on the YouTube channel, the Probe Software YouTube channel, we're doing short, like 10-minute tutorials of specific features. And then we're also doing these webinars, these extended webinars for kind of a more in-depth look at the theory behind various things, So you can make a suggestion for another webinar, which are typically 40 minutes per presentation. Sorry that I broke the record. But then we also are looking for suggestions for short 10-minute tutorials. We have a
yeah,
number of consultants that are happy to make these tutorial videos for YouTube, and they're really nice for just kind of stepping through things and looking at the mouse click by mouse click, sort of like you did with the PictureSnap app. So yeah, that was great.
yeah. Okay, good. Then I will conclude this webinar with that, and I hope you all have a good day and see you for the next webinar, or
Right,
otherwise maybe on the forum. That is also a great way to ask follow-up questions, or there are more tutorials. So
right.
yeah, have a good day from both of us and see you next time.